Good. So today we're going to be talking about quark-quark scattering in QCD, which we learned how to do the Feynman rules for last time. Okay, and the first thing we should say is we should admit that this is actually not directly observable because quarks aren't directly observable. Quarks are bound into hadrons. And so the calculation we're about to do isn't going to be something that we can just observe or verify directly. We're going to have to do some more things to it after we're done. In fact, what we really see is that you have two hadrons, and in modern, let me call it hadron plus hadron, because it's usually quark proton or proton antiproton. Okay, so P plus P, for example, at the Large Hadron Collider. And you get out a jet of particles and another jet of particles that are coming from the final state quarks. So what we're actually going to be calculating today is what's called the microscopic or hard scattering process. And to make things nice, I'm going to have in mind specifically an up quark and a down quark scattering to an up quark and a down quark. And the reason for that choice is kind of similar to why, for example, we might look at mu plus mu minus goes to, or E plus E minus goes to mu plus mu minus. It's because there will be fewer Feynman diagrams. In fact, there is only one Feynman diagram for this case, which looks like that. Okay, so here's our up quark. And there's the up quark in the final state. And this is the down quark, and this is the down quark in the final state. And the gluon is traditionally written as a springy line as opposed to a wavy line. Let's put momentum P going this way, and I'm going to call it P prime for this one. And then coming out is going to be K and K prime, which means the momentum in the gluon direction is P minus K. Okay, and so that's it. That turns out to be the only Feynman diagram at lowest order in QCD. We'll talk about later what happens beyond leading order in QCD. But to calculate it, let's assign momenta and spins. And now the new ingredient that we didn't have in quantum electrodynamics is we also have colors. Okay, so here's our little table. We have for each particle a momentum, a spin, the spinner, and then the color. Okay, so there's the initial up quark with momentum P, spin, I'm going to call it S1. The spinner is UPS1, but we're going to call that U1 for short. And then the color is I, which can be one of three things, but we're going to call it I. Okay, then there's the initial down quark with momentum P prime, spin S2. And so its spinner is going to be called U2. That's supposed to include the information about both P prime and the spin S2. And then its color is J, which again will be 1 to 3. Then there's the final up quark, with momentum K, spin S3. Its spinner is going to be U bar 3, and its color will be L. And then there's the final down quark, K prime, with spin S4, spinner U bar 4, and yet another color, M. So the colors can all be completely independently different in general. All right, so we've written down the information about the particles, we've drawn the Feynman diagram, and now we can write the matrix element, the reduced matrix element, in Feynman gauge. That's going to affect what we write down for the gluon propagator. Okay, so here it is. Reduced matrix element is, we follow the up quark line and we get U bar 3 minus IG3. That's the value of the QCD coupling, traditionally called G3 or sometimes GS for strong. And then there's a gamma mu factor. Let's label this mu and this nu. But now there's the matrix TA, and it's Li. Okay, so those things come from the colors that we read off the table. And so we're following it backwards. We're starting from color L for this up quark, and we're ending on color I for this up quark. Okay, and then finally at the end of that line, there's a U1 spinner. Okay, then we can follow the down quark line similarly, and that looks like this. U bar 4 minus IG3 gamma nu TB MJ from the colors, and then U2. So maybe I should have also, the Feynman diagram's getting a little crowded, but I should label this gluon line here as A, and this one as B. Okay, and then we've done the fermion lines, and finally we have to do the gluon propagator. So that factor looks like this, minus IG mu nu delta AB over P minus K squared. So remember, gluon propagators don't change the gluon color. That's why it's delta AB. And in Feynman gauge, it's just proportional to the metric G mu nu. Okay, any questions on that? Somebody ask a question so that I know you're there.
I mean, I don't have any questions, but it seems pretty straightforward.
Okay, good. All right, and now we can just clear out the factors and get I G3 squared. I'm pulling out the matrices for the color. Oops, that should have been an I. TALI. TAMJ. Notice I used the delta AB to say that, aha, this A and that B are actually the same. And so I'm summing over them. So now I'm just summing over one of them. Okay, and then the rest of it looks exactly like QED for, let's say, E minus scattering. So we're going to be able to exploit that fact to save us some labor. So there's a 1 over T, a Mandelstam T there. All right, so this is in fact the same as QED for, let's say, E minus mu minus goes to E minus mu minus, but with, instead of writing down E squared like we would in QED, now we're writing down G3 squared times this pair of color matrices that we have to do something with. Okay, so the first thing to notice is how many different color combinations are there? There are 3 times 3 times 3 times 3. So there are 3 to the 4th equals 81 possible color combinations. And we certainly don't want to keep track of all 81 of them separately, even though we could. And even though a lot of them actually turn out to be 0, because one or more of the corresponding matrix elements will turn out to be 0. But really what we want to recognize is that we need to average over the initial colors and sum over the final colors, because they're not going to be observed. So need to average over initial colors. The initial colors are I and J. And sum over final colors. Those are the L and M. And so what we really want is 1/3 sum over I, that's averaging over I, 1/3 sum over J, sum over L, sum over M of this reduced matrix element complex squared. And when we do that, then we're going to plug into the formula for the cross section. So let's just concentrate on the colors for a while. So our reduced matrix element squared is equal to G3 to the 4th power, TALI, TAMJ, TBLI, TBMJ complex conjugate, times, I'll write M hat here for the part that's just the same as in QED. So M hat is this stuff, U bar 3, gamma mu U1, U bar 4, gamma mu U2, times 1 over Mandelstam T. Okay, that's the same as in QED. All right, so we need to do this big color sum. And the first thing to notice is that TB, let's look at the complex conjugate part, the part that came from the complex conjugate. So TBLI, TBMJ star. Okay, and that's equal to TBIL, TBJM. So why is that? That's because the T's are Hermitian. That's a crucial fact. And so that means if I take the complex conjugate and the transpose, I get back the same thing. So here I'm taking the complex conjugate, so I know I can rewrite that in terms of the original T's. If I take the transpose, which means interchange I and L, that's what I did here, and interchange M and J, that's what I did here. So in any case, that's an identity. And so now the color factor part of our reduced matrix element is 1/3 sum over I, 1/3 sum over J, sum over L, sum over M, TA, LI, TA, MJ, TB, IL, TB, JM. I should say the reason we used B rather than A is back up here, we were summing over the A's. And so when we sum over them again, we want to use a different letter so that we don't get this A's confused with those B's. Okay, now we stare at this for a little while and see how the color factor indices are tied up, we notice we've got Li, and then here we've got IL. So together that makes a trace of this TA and this TB. And the same thing here, we've got TAMJ and then we've got JM. So we can rewrite this whole thing as 1/9 from the 1/3s, trace TATB, and then another trace, TATB. So the good thing about that is that when we were talking about group theory representations, we gave these things names. This is equal to the index of the relevant representation, which is the 3 representation times delta AB. And this is also. Okay, and the index of the 3-dimensional representation, we said was 1/2. These are things you can look up in tables, what the indices of various representations are. And so this whole color factor is 1/9 times 1/2 squared times delta AB, delta AB. And so what we're really doing is we're summing the identity, or 1, over all 8 of the ABs, which are the colors. And so this is the dimension of the adjoint representation, which for QCD is equal to 8. Okay, and so the whole color factor is, it just turns out 2/9. So that's what you get from putting in all the color matrices and doing the averaging and summing, averaging over initial state colors and summing over final state colors. Okay, and meanwhile, the reduced matrix element hat squared part is same as QED after stripping off the e to the 4th part. So stripping off e to the 4th, that came in QED. And so we get the final answer for the reduced matrix element squared. It's traditional to put a bar over the whole thing. That just means that you're summing over everything for the final state, averaging everything for the initial state. I'll write it explicitly as 1/9 sum over colors, 1/4 sum over spins, matrix element squared. And when you plug in our answer from QED, we get 4g3 to the 4th over 9 s squared plus u squared over t squared. The t squared in the denominator, of course, is reminding us that this came from a t-channel diagram. Okay, so now we could write down the differential cross-section just by plugging into the relevant formula. It's 1/32 pi s reduced matrix element squared with sum and average. And so that's going to be 2 pi over 9 alpha s squared plus u squared over t squared, where here alpha s is the strong interaction version of the fine structure constant. So it's, instead of e squared over 4 pi, it's g3 squared over 4 pi. Okay, so this is just like alpha for quantum electrodynamics. Okay, and then you could write this in terms of the Mandelstam t variable. So d cos theta, this is a useful formula for massless kinematics, is 2 over s differential with respect to t for massless kinematics. So we finally get d sigma dt is 4 pi alpha s squared over 9 Mandelstam s squared times s squared plus u squared over t squared. So sanity check, it is indeed a 1 over energy squared, because we're taking the differential of a cross section with respect to another energy squared. Okay, so that's a useful formula, although it's, as I mentioned before, it's not ready to be compared with experiment directly yet, but it's one of the ingredients that we will have to figure out how to use later. Okay, any questions on this so far? We've done up, down scattering. Okay, so I want to spend a little bit of time before discussing how to actually use this formula. I want to discuss what will happen if you do radiative corrections to it, meaning loop diagrams. We've only done the lowest order diagram. And that's important because since alpha s is not a small number, it's more like a tenth at the z mass, for example, we need higher order corrections in general to get a good answer. And so let's write down what some of them are. And I'm just going to include things at one loop order. Okay, so let's just draw all the diagrams we can think of at one loop order. Here's some. Here's one class of diagrams. So instead of exchanging one gluon, now I'm going to exchange two gluons. So there's that diagram, and then this one's a different diagram where the two gluons cross each other. Okay, so these are known as box corrections. They are a sub case of one loop corrections. Here's some more one loop corrections. So I'm still exchanging one gluon, but now I exchange a gluon like that. Or like that. Or here's another one you can draw. Because there's a 3 gluon vertex, you can draw that one. Or this one. Okay, and so these are called vertex corrections. Or I can't spell vertex today. And the reason they're called vertex corrections is basically this part can be viewed of as a correction to the single vertex. This is a correction to that vertex. This is, again, another correction to this vertex. And this is another correction to that vertex. Okay, but there's more. There's things like this. So these are corrections to the external lines of each of our quarks. Okay, and these are quark wave function corrections. And then finally, there are corrections that look like this. So because a gluon can interact with itself, we have that diagram. Or we can have a diagram where the gluon being exchanged decides to split into a quark anti-quark pair. Okay, or it turns out, going with the first diagram in that line, there are other diagrams that look like that, where these are the infamous ghosts that don't appear at tree level when you have non-loop corrections. They're there to cancel the unphysical degrees of freedom of the gluon line. Okay, so these are gluon wave function corrections. All right, now each one of these, all of these diagrams has a loop momentum that's undetermined that you have to integrate over. So there's an integral d4L. L is a 4 momentum for the momentum going in the loop, like that, for example. And so you have to do an integral. And this might diverge. In fact, it very often does because of the behavior at large energies. So first of all, you can tell how bad things are by doing power counting, and I'm going to do the box corrections as just a sort of an example. The box corrections, it turns out, don't diverge. So let's see why that is. The box corrections are okay. They're finite. And one way to see that is because it has vector propagators, gluon propagators, which all look like this at large energy, 1 over L squared for each gluon. And for each fermion, there's an L slash plus a mass over L squared. I'm forgetting about the masses because I'm just worried about what's happening at high energy. So this is for each quark. And so if you put that all together for the box diagrams, there's each one of them has 2 fermions and 2 gluons. Okay, and so this will be integral d4L, L slash, L slash. I'm just doing power counting, so I'm not worried at all about the fine structure of this. L squared to the 4th power, which goes like an integral of an energy divided by an energy squared. And because the energy squared is in the denominator, this is finite. Okay, so you can put in all the bells and whistles and traces over gammas and color pieces and all that. But in the end, all that really matters is how do propagators scale with energy? And that shows the box corrections are finite. But the other ones are not finite. For example, these ones are certainly not finite. So for those, you need a cutoff of your integral. And there's a hard way and an easy way to do it. Actually, they're both hard. Okay, but what you're really doing is you're saying, we don't know what's happening at very high energies, so we have no business integrating over very high energies. Something else will happen there. And so we're going to only integrate for energies less than some mass scale. Okay, and this is some very large mass. And maybe it's the Planck mass, which is quite large indeed compared to everything else. So roughly 10 to the 19 G. Okay, but we don't really know what that cutoff is. We have no way of knowing. I should mention that that's not exactly how people do this in practice. In practice, they do a very weird thing called dimensional regularization. Despite being very weird, it's also much easier. And in dimensional regularization, what you do is you change, instead of integrating d4L, you do your cutoff to the power of epsilon times an integral over 4 minus epsilon dimensional space. So it's hard to even imagine. We certainly don't live in a fractional number of dimensions, but nevertheless, that's what you do. And then you take epsilon goes to 0 at the end of the calculation. And this has the same effect as if you put in a cutoff, it turns out, but it's much easier as far as algebra. despite the fact that it's relatively much easier, it's still pretty hard. And so we're not gonna have time to cover that in this course. So the bottom line is, if you take all these diagrams and you do everything carefully, I'm just going to quote the answer so you can see what it looks like. Do everything carefully. You get a differential cross-section, which is equal to the tree one, that is the one we actually calculated. And I'm going to write it as a function of g hat. I'll explain what g hat is in a minute. Times 1 plus every loop diagram has 2 more powers of g hat. And then there's some group theory factors, which turn out to be 11/3 the Casimir of the adjoint, minus 4/3 the sum over all the quarks for each of their indices, which turn out to be 1/2, multiplied by a logarithm of the cutoff mass scale divided by m bar, I'll explain what that is in a minute, plus something that we're not going to worry about, I'll call it x. Okay, plus order g hat to the 4th power. All right, time for me to explain what g hat and m bar are. G hat, all I've really done is I've taken G3 and I've renamed it g hat. And the reason for that will be explained and why would I make that choice of notation? I'll explain why in a little bit. Okay, but so g hat is just what I used to call G3. And then the other thing is m bar has units of mass, as the name suggests. And it's built out of things like Mandelstam S, Mandelstam T, the quark mass squareds, and I guess that's actually it. Okay, so it's, and it's something very complicated, but it's something that has dimensions of mass. You can work out exactly what it is, but I'm not going to tell you exactly what it is. It's some very complicated thing. And x, the only thing we need to know about x for today is it is finite as you take the cutoff to infinity. Okay, so in other words, what we've really done here is we've separated out the part that's bad when the cutoff is large. That's the would-be divergence. And it's a logarithmic would-be divergence. You can find that by power counting. The x is something that you can calculate, and people have calculated it, but it's finite as m goes to infinity. And same with the m bar. Okay, so this is capturing all the information about how badly these loop diagrams are trying to diverge. Okay, and so that's the answer that you get. All right, so now you could say, well, what is the cutoff? And I want to admit explicitly that we do not know, and we have no way of knowing. It's the energy or mass scale at which something is happening to change the loops so that you shouldn't integrate over them. But if we knew what that was, then it wouldn't be the cutoff anymore. Then we'd include that in our theory, and then we'd have a different cutoff at some much higher scale than that. So by definition, we have no way of knowing what the cutoff is. So nobody knows. So at first, it looks like we're in big trouble because we've got an answer here that depends on something that I just admitted to you we have no way of knowing. The way out is we're going to absorb this into a redefinition of the couplings. So absorb the unknown m into a redefinition of the couplings, which are also arbitrary, but at least those we could measure. So in this case, the coupling is G hat. Okay, any questions so far? We're doing renormalization, which is a notoriously tricky business.
Yeah. As far as like, is there theoretically a way that we could know what M is if we could just probe a high enough energy scale, or is it just impossible to even grasp?
Well, so you can imagine we probe some very high energy scale and we discover some new particle or some new phenomena at very high energies, and we say, aha, that's what changes the behavior of the momenta and the integrals. That's what it is. But then at that point, we would define a new theory with that new physical effect built in.
Hmm.
And then we'd need a new cutoff for that theory. So
Right. So yeah,
sort of by definition, you never know what the cutoff is. If you
gotcha.
knew, then you would redefine your theory to include it, and then you'd have another cutoff.
Gotcha.
Yeah. Okay. And in this case, at least for QCD, we don't really know. There are ideas, but we don't really know. Okay. So what we do is we define a renormalized coupling. And I'm going to call it G, and G is going to be a function of some mysterious quantity that I'm going to call mu by the following. G hat, which was our coupling, is equal to G mu times a correction factor that looks like this. 1 minus G mu squared over 16 pi squared. And then we put in the same exact group theory factor. So it depends on the sum over the index of the quarks in their representation times a logarithm of the cutoff mass, but now divided by mu. And I'm not including the x here. Okay, and then I could do plus dot 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 if I did more loop diagrams. Okay, so this is a very sneaky thing to do. What is mu? Mu is equal to a new arbitrary mass scale, not the cutoff. And it's arbitrary and we get to pick it. So we do know what that is by definition, because it's something we choose. This is known as the renormalization scale. It's a mass scale or an energy scale. Okay, and that's why I changed notation and called the coupling G hat, is because I wanted to define this new G that doesn't have a hat, because I don't want to write hats for important things later. Okay, so just to summarize, the original coupling G hat is now going to be called the bare coupling. And G of mu, which depends on an arbitrary scale mu, is the renormalized coupling. So it looks doubly arbitrary because it depends on the cutoff that we don't know, and another arbitrary scale, that mu, that we pick, but we can pick it to be anything. Okay, so the first thing to notice about this is we can invert this. So you can write the renormalized coupling as the bare coupling times 1 plus G hat squared over 16 pi squared. And then there's the same group theory stuff, 11/3 CA. By the way, somebody, Wilczek and Gross and Pulitzer won the Nobel Prize for computing the 11/3 CA stuff. Okay. So what is the point of doing all this seemingly arbitrary stuff? Why do this? The answer is because now let's write the total differential cross-section in terms of G rather than G hat. And when you do that, you get the following. Okay, I'm taking G hat and I'm using this big ugly mess to replace G hat by G everywhere. And so I get D sigma tree of G, not G hat, times G hat over G to the 4th power times 1 plus, the reason it's G hat over G to the 4th power, by the way, is because hidden in here is a G to the 4th, right? So we know everything scales like G hat over G to the 4th power times 1 plus some stuff times logarithm of cutoff over M bar. Okay, and G hat over G to the 4th power is 1 minus 1/4 stuff logarithm of M over mu, all of that to the 4th power. So now if I expand out in the stuff, I find out this is the tree level differential cross-section times 1 plus, I'm going to rewrite stuff that looks like it's the same, but there's going to be a subtle difference. So 11/3 CA minus the other group theory part, logarithm of mu over M bar, plus higher order stuff. So here's the great thing, is that in this new formula, we actually know everything, right? It's easy to calculate. We just did it. We calculated this already. So we know this because we just know, we calculated and we plug in the G rather than G hat. And then the rest of this has been engineered so that there is no more cutoff dependence. Okay, so people have calculated the M bar. We get to choose mu to be whatever we want. So we certainly know that. So it's sort of magical that we've gotten rid of the thing that we don't know, the cutoff scale, in favor of a scale that we do know because we get to pick it, and a scale that we get to calculate. Okay. The only drawback to this is we don't know what G is, but then you can do one experiment that measures G, and then once you know G, then you can use every calculation for every other experiment that you can do to verify whether that was in fact the correct G. One experiment is good enough to get you G. All right, so now you can say, okay, we still got this scale mu, what should we pick mu to be? Okay, so what should we pick for mu? And one answer is anything you want, does not matter, because if you choose a value for mu, then you just have to determine the G for that mu, and everything's fine. You could choose, seemingly, you could just choose mu equals the cutoff, but we don't know what that is, so you can't do that. Not that there's any reason you'd want to. You could choose it to be something roughly like what the cutoff is. Maybe it's the Planck scale, who knows? But that's a bad choice. So why is it a bad choice? It's a bad choice because then logarithm of mu over M bar would be roughly logarithm of M Planck over M bar. M bar is something that's built out of Mandelstam S for the process you're doing. So maybe that's 1 TeV or something like that. And so this would be a large logarithm. So this would be 35 for m bar, let's say 1000 GeV. Just plug in the number for m Planck. So the problem with that large logarithm is then you've got a large logarithm multiplied by a number of all this stuff is basically of order 1, and then your series is not convergent. So instead, what you want to do is you want to choose mu so that this logarithm is not large. And an easy way to do that is just choose it to be the same order as m bar. So instead, want small logs. So choose mu to be roughly of order m bar. And the great thing is it doesn't matter. You don't have to know m bar exactly. You can just make an estimate for it. So then the logarithm will be small. Okay, and so d sigma will be the tree level value times 1 plus small calculable corrections. So maybe I'm exaggerating when I say small. What I really mean is not too huge. So because for QCD, it's not at all unusual to find out that the first correction is maybe 20 or 30% as big as the tree level, the original tree level part. So perturbation theory isn't converging very quickly, but at least it's not wildly divergent. Okay, so what I just told you is sort of the baby version of how renormalization works. Let me tell you how well it works, which is sort of an amazing fact. Is that this works beyond what I said at one loop order. In Yang-Mills theories, meaning non-abelian or even abelian gauge theories, they have the special property. This was shown by Tuft and Veltman, for which they also won the Nobel Prize. They showed that if you do the following redefinitions, you can absorb all of the cutoff dependence. So G hat, the bare coupling, is equal to a renormalized coupling times 1 plus a sum from n equals 1 to however many loops you calculated, let's call it L, times some numbers, g to the 2n power, times some polynomial of logarithms. Okay, so L equals number of loops. And then at the same time, you do the same thing for the masses. So there are bare masses, which are equal to renormalized masses times, again, 1 plus a correction that goes over the number of loops. Okay, the number of each loop comes with an extra 2 powers of the coupling. And then there's some other polynomial, again, in logarithms of the cutoff divided by the mass scale. Okay, and so of course I could always do this definition, but here's the amazing fact: is this eliminates the cutoff, that is capital M, dependence, not just in, for example, the process that we actually calculated, but in all processes. So I could do gluon quark scattering or gluon gluon scattering in all processes at L loop order, meaning the diagrams have L loops in them. Okay, don't try to prove this at home. It's not easy to prove. That's why they got the Nobel Prize for it. And this is for fixed constants Bn and Cn. okay, and polynomials. So polynomials and logarithms. So if you're in a theory where you have just one coupling and one mass, that means you only have to do 2 experiments. 2 single experiments will tell you what G and M are, and then every other experiment you get is a test of that theory. Okay, so let me just write down observables. What this means is that observables are functions of the renormalized coupling, the renormalized mass or masses, M of mu, and logarithms of the renormalization scale, which we get to pick, and M bar, which are calculable combinations of things like Mandelstam variables and masses. And their characteristic size is whatever the characteristic energy scale of the problem you're doing. Okay, and this is what renormalizable means. Is that it obeys this amazing fact. You might have thought, maybe I just keep doing different processes and I keep getting different combinations here, right? That's what I would have expected if you asked me, but it turns out the same constants in these redefinitions between renormalized or running couplings, we'll talk about running next time, and the bare couplings, the same exact redefinition gets rid of the cutoff dependence in all processes that you could ever calculate. Okay, so we're out of time for today, but next time we will talk a little bit more about renormalization, and then we'll also talk about gluon-gluon scattering. And then finally, we'll figure out how to actually turn this into observables for hadron colliders, like the Large Hadron Collider. All right, thanks. Any questions?
Did this look like black magic to you the first time you saw it?
Yeah, it still looks like black magic to me.
Okay, that's good.
Despite that, I've actually done things like this to 3-loop order and checked that it all works, and I trust that it all works. And in fact, you can sort of turn it around and use this as a check of various calculations, and it's amazing, it works. Yeah, it definitely looks like magic. Any other questions? All right, if not, I will see you all on Wednesday, same bat channel.